Welcome, curious minds, to another essential exploration. Today, we're really navigating the rapidly evolving landscape of electrical grids.
It's changing so fast.
It really is our topic. It's an in-depth look at introduction to smart grid concepts, which,
Yeah.
I mean, it's fundamental for anyone in electrical engineering.
Absolutely essential. Yeah.
Our mission here is basically to break down the core ideas, maybe clarify some key terminology, and just get a clear picture of why this transformation isn't just, important, but actually necessary.
Hmm.
So we'll explore this material step by step. Think of it like a focused training session. And remember, when we reference specific content, we'll say, in the slide you can see, just to refer to that visual information.
And I have to say, I'm really excited about this topic. Its relevance to, well, to current and future energy systems is just huge.
Right.
Understanding the smart grid, it's really key to navigating the whole future of energy. It touches, every single aspect, from the biggest power plants right down to, your home. It's not just an upgrade. It's a real foundational shift.
Okay, let's dive in then. We really have to start with the basics, the bedrock question. What is the main objective of any electrical supply system, fundamentally?
Good starting point.
Yeah, because in the slide, you can see that the overarching goal is always to co-optimize. Now, that sounds technical. So what does co-optimize actually mean in this context? Why is it so central?
That's a great way to put it, because co-optimize, yeah, it's right at the heart of running a grid. It basically means trying to achieve several critical goals all at the same time. And crucially, these goals often pull against each other.
Oh, okay. A balancing act.
Exactly, a delicate balancing act. And you're doing this for whatever mix of generation capacity you have available and whatever the demand patterns look like at that moment. It's not about maxing out one thing. It's about finding that optimal equilibrium.
So what are these objectives that need balancing?
Okay, so first, there's the reliability of power supply. For an engineer, reliability means, pretty concretely, how often do outages happen and how widespread are they?
Right. Keeping the lights on.
Exactly. Think about daily life. Consistent supply is just paramount. Outages, even short ones, they impact everything, right? Hospitals, factories, your internet. The economic hit can be massive. And historically, the traditional grid, well, it's always been a challenge to keep reliability super high. It's a constant battle, especially as demand keeps growing. It's sort of like keeping a huge old train network running perfectly on time all the time.
Makes sense. What's next?
Second is the quality of power supply. This is a bit more technical. It's about the shape of the voltage waveform, the frequency, and the phase angle.
Okay. Why are those important?
Well, each one is critical. Stable voltage means our devices, especially sensitive electronics, work correctly. No flickering screens or crashing computers. Consistent frequency is vital for things like big motors and generators to stay synchronized. And the right phase angle, that's key for efficient power transfer across the network. Poor quality means things malfunction, wear out faster, overheat, waste energy. It leads directly to higher costs and less reliability. So it's not just having power, but having good power.
Got it. Reliability, quality. What's the third leg of the stool?
The third, and this is always a major constraint, is power affordability for the consumer. The economics. Look, achieving top-notch reliability and quality is great, but it has to be balanced with what's economically viable. For consumers, yes, but also for the utilities.
Because upgrades cost money.
Exactly. If electricity gets too expensive, it hurts the economy, impacts industries, creates social issues. It's a basic necessity. So what's really fascinating here is how these three, reliability, quality, affordability, they often conflict. Boosting reliability might mean costly upgrades, driving up prices,
Right.
achieving all three simultaneously, perfectly. That's the holy grail of grid operation, and that's really what the smart grid aims to do better, more dynamically.
That really sets the stage for the complexity involved. Okay, let's pivot a bit. Let's talk about the traditional grid. In the slide, you can see it's often called one of the biggest engineering feats of the 20th century. Why is that? What made it so revolutionary?
Oh, that statement is absolutely true. The traditional grid was, a massive, unprecedented achievement. It literally electrified the world. It drove industrial revolutions, enabled modern life as we know it, connected communities. The scale, the complexity, the societal impact is just staggering. Really a testament to ingenuity.
So what was its core design philosophy?
It was remarkably consistent, actually. First, it relied on centralized generators. Think huge power plants, coal, nuclear, big hydro dams, often located pretty far from cities and towns where people actually use the power.
Okay, big plants far away.
Right, which meant you needed unidirectional electricity transport. Power flowed mainly one way, from those big generators onto high-voltage transmission lines, stepped down to lower-voltage distribution lines, and finally into homes and businesses. You can picture it like a one-way highway system for electricity. Big source, many destinations.
And how was it controlled?
Through centralized control centers. Their job was to gather, well, relatively limited information, mostly from key hubs like substations. It was more of a supervisory model. Operators watched key points and reacted, often manually making adjustments.
So it was ingenious for its time, but you mentioned it's a century-old design.
Exactly. And despite its brilliance, it's facing huge pressures today. Which leads us to the critical question. Why can't this incredible design just be scaled up, maybe tweaked a bit? Why does it need such a radical rethink for the 21st century? What's fundamentally different now?
That's the perfect transition. It sounds like the whole approach needs to evolve.
Yeah.
So in the slide, you can see this comparison laying out what is changing. Let's walk through that. What are the biggest transformations pushing us from the traditional model?
Absolutely. This comparison really crystallizes why just making the old grid bigger won't work. It highlights the fundamental shifts.
So first up, energy sources.
Right. Traditionally, mostly centralized, fossil fuel-based, big predictable plants. What's changing? Massive diversification. We're integrating renewables, distributed sources, think rooftop solar, huge wind farms.
So lots of smaller, scattered sources instead of a few big ones.
Precisely. And that fundamentally changes where power comes from, when it comes, and how you manage it. It's not just about going green. It's a total re-architecture of the supply side.
Okay, and that leads to the next point, energy source variation.
Yeah. Traditional sources. Fixed, definite nature. Predictable. You could control them. What's changing? Huge variability with renewables. RES. Solar power depends on the sun, clouds. Wind power depends on, well, wind speed.
They're intermittent.
Exactly. Intermittent and not easily controllable like a gas plant. This creates massive new demands for grid flexibility. The grid needs to react instantly, second by second, to these fluctuations.
What about the demand side? The demand nature.
Traditionally, we had, fairly simple loads, lights, motors. Now, load behavior is changing fast. We see more inverter behind load, that's power electronics mediating consumption. Lots more silicon loads, all our gadgets, data centers, plus big new loads like battery storage, BESS, and of course, electric vehicles, EVs.
How does that change things?
Well, electronics can affect power quality differently, and EVs, that's potentially a huge new demand that needs careful management, or it could overload local parts of the grid.
Which connects to demand variation, right?
Right.
Limited elasticity changing to elastic demand.
Spot on. Traditionally, you, the consumer, didn't really change your usage based on grid conditions or price. Demand was inelastic. Now, we're seeing the rise of elastic demand. People can shift usage, think smart charging for your EV when power is cheap, or smart thermostats adjusting slightly.
So demand itself becomes a tool for balancing the grid.
Exactly. It's a game changer. You're not just adjusting supply, you're shaping demand too.
And that ties into consumer interaction, moving from passive to active prosumer.
Perfectly. Old grid, you just paid your bill. New grid. You might have solar panels, a battery, smart appliances. You become a prosumer, producing and consuming. You can generate, store, maybe even sell power back. It completely changes the relationship with the utility.
Let's talk tech. Transmission technology. Less FXETS HVDC changing to more. What are those?
Okay, so FSETS are flexible AC transmission systems, and HVDC is high voltage direct current. Traditionally, less common. Now, we're using them much more. FCTS let you control power flow on AC lines better, boost capacity. HVDC is great for moving lots of power over long distances, like from offshore wind farms or connecting grids that aren't synchronized.
So better highways for electricity, essentially.
Kinda, yeah. More controllable, more efficient highways, especially for renewables that might be far from where the power is needed.
And what about IBR integration technology? That sounds like IT stuff. Minimal automation to more automation.
Yeah. IBR is inverter-based resources. Think solar, wind, batteries connected via inverters. And yes, the IT part is key. Traditional grid had minimal automation, lots of manual checks. What's changing? A massive move to automation, remote control, sensors everywhere, communication networks. This is the smart part, really, using ICT information and communication tech to make the grid intelligent.
Which must relate to power flow changing from unidirectional to bidirectional.
Absolutely crucial point. Traditionally, power flowed one way, generator transmission, acquisition telemetry, you. Now, with rooftop solar and other distributed generation, power can flow backwards onto the grid from homes or businesses.
That sounds complicated.
It is. Distribution lines weren't designed for two-way flow. It creates huge challenges for things like voltage control and protection systems.
Yeah.
You need a whole new way of thinking about managing and protecting the grid.
And that brings us to stability issues. Traditional ones versus new ones like resonance and control interaction.
Right. Old grid stability issues were mainly about frequency, voltage, keeping big spinning generators, synchronized electromechanical stuff. Now, with all the power electronics, the inverters for solar, wind, batteries, even modern loads, we see new issues. Things like harmonic resonance, complex interactions between different control systems. It's like adding electronic instruments to a traditional orchestra. You need new ways to keep everything in harmony.
Finally, the power market. Monopoly to competitive.
Big shift. Traditionally, often a regulated monopoly utility, maybe long-term contracts, PPAs. Now, we're moving towards competitive markets.
Yeah.
Lots of different players, generators, storage operators, aggregators, even you as a prosumer buying and selling power and services. This introduces new economic signals, drives innovation, but also demands more transparency and complex market designs.
Wow, okay, connecting all that. It's not just tweaking the old system.
Not at all. If you connect this to the bigger picture, these changes aren't incremental. They represent a true paradigm shift, a fundamental rethinking of how we generate, deliver, and use electricity. It's becoming a much more complex, dynamic, interconnected system.
That breakdown really clarifies the scale of the transformation. It paints a picture of the traditional grid-facing, well, a perfect storm of challenges. So in the slide, you can see this list of challenges. Can we dive into those? What are the specific pressures forcing this move to a smart grid?
Exactly. These aren't just abstract problems, they're concrete issues pushing the need for change. Let's look at them.
First up, electricity losses.
Yeah, this is a big one, especially in developing economies, but significant everywhere. Losses can be technical, just energy lost as heat in wires over distance, or they can be non-technical, which often means theft. Either way, it's wasted energy and a huge economic drain. Utilities just can't afford it.
Then, aging infrastructure. We hear about this a lot.
We do, and for good reason. A lot of grid equipment, transformers, cables, poles is old, sometimes 50, 60 years or more, well past its design life. Deferred maintenance over decades means it's just more likely to fail.
Leading to blackouts.
Exactly. We see major blackouts attributed to aging equipment even in developed countries. It disrupts lives, businesses. It's a massive reliability issue.
What about rising demand in developing economies?
The sheer scale is the challenge here. These economies need to add huge amounts of new capacity and fast just to provide basic access and support growth. They often need to build out infrastructure quickly, sometimes leapfrogging older tech.
And intensifying demand around peak hours. The peak strain.
Right. This is about efficiency. The grid has to be built to handle the absolute highest demand, even if that peak only lasts a few hours a day, maybe on hot summer afternoons.
So the rest of the time, a lot of capacity is just sitting idle.
Precisely. It leads to underutilized assets. Think expensive peaker plants that only run a few dozen hours a year. It's like building a giant stadium for just one game. Very inefficient economically.
Which links to the need for flexibility sources, right? Especially with renewables.
Directly linked. As we add more variable renewables like wind and solar, the grid needs more flexibility. It needs resources that can ramp up or down very quickly. It could be fast-acting gas plants, batteries, or even demand response to balance out those unpredictable fluctuations in supply second by second.
Okay, what about the distance issue? Long distance between offshore wind and demand centers.
Yeah, this is a practical engineering challenge. Offshore wind farms can generate huge amounts of clean power, but they're, well, offshore. Getting that power back to land and to the cities where it's needed, often hundreds of kilometers away, requires specialized, expensive, high-voltage transmission, like HVDC cables we mentioned. It's a major cost and technical hurdle.
And then there's potential power quality issues and backflow. We touched on this.
We did. Distributed generation, like rooftop solar, can cause problems locally, like voltage getting too high on a neighborhood circuit. And if enough power flows backwards onto the higher voltage system, it can cause instability because the system wasn't designed for that reverse flow. It messes with protection schemes.
Lastly, uncontrolled charging of electric vehicles.
This is a looming giant. Imagine millions of EVs plugging in around the same time, say, when people get home from work. That's a massive sudden load increase. If it's uncoordinated, it could easily overwhelm local transformers and distribution feeders.
So we need smart charging.
Absolutely. Solutions that manage when and how fast EVs charge, spreading the load out, maybe charging when there's excess renewable energy. Otherwise, we'd need incredibly expensive grid upgrades just to handle that peak.
There really is a complex web. You mentioned these challenges often cluster.
They do. In the slide, you can see they group into things like rising demand, aging infrastructure, more renewables, and distributed resources, EVs. And they interact. Aging infrastructure struggles more with rising demand and the variability of renewables. EVs add strain to local distribution already dealing with backflow from solar. It's this interconnectedness that makes a piecemeal approach insufficient. You need a holistic solution.
Which is where the smart grid comes in. So let's formally introduce it. In the slide, you can see we look at its origins. Interesting that it's a bit mysterious, but the term gained light around 2003 with Grid 2030.
Yes, it's quite interesting. You can't really point to one person or one moment and say, that's when the smart grid was invented. It was more an evolution of ideas bubbling up in the industry for years: grid modernization, automation, advanced metering.
But 2003 was a key moment.
Definitely. The term smart grid really took off around then, largely thanks to that U.S. Department of Energy report, Grid 2030. It painted this vision for a modernized grid using advanced tech. It got people talking.
And then the IE paper in 2005.
Right. The article Towards a Smart Grid by Amin and Volenberg in IE Power and Energy magazine, that really helped flesh out the concept and its potential. Foundational stuff.
And there's this common belief mentioned that it will revolutionize the electricity business model.
Yes, there's this strong underlying belief, almost an assumption, that the smart grid isn't just a technical upgrade, but something that will fundamentally change how the electricity business works. A model that's been pretty stable for, 75 years or more. Centralized generation, one-way delivery, monthly bills.
Which raises that important question. What does it actually mean for a business model to be revolutionized in such a core industry?
Well, I think it means moving from that simple model, utility makes power, sends it, you pay, to something much more dynamic and interactive. It means consumers becoming producers, prosumers, energy storage playing a role, utilities potentially becoming platform managers or service providers rather than just commodity sellers. Think dynamic pricing, energy services, managing two-way flows. It impacts revenue, investment, customer relationships, everything. It's a shift from selling electrons to enabling and managing complex energy flows and services.
That's a huge shift. So we keep talking about smart. In the slide, you can see the question.
Wow.
What is smart in smart grid? Because as engineers, we know the grid was already pretty clever, right?
Absolutely. That's a great point. The electrical grid has always been smart, in a way. It's been constantly evolving, adapting to new loads, new generation for over a century. It's an incredibly complex, self-regulating machine already.
So what's different now? Why the emphasis on smart?
The difference is the pace and scale of the changes hitting it now. New challenges and the associated changes, they just keep coming. But the issue is when these changes are really rapid and massive, like this whole energy transition we're in, the traditional ways of adapting just take too much time.
The system can't keep up organically.
Sort of, yeah. The pace of integrating renewables, the digitalization, the rise of EVs, it's unprecedented. So for the last decade or so, we've been talking about smart grid. Initially, maybe the focus was more heavily on distribution, fixing losses, automating substations.
But now it's broader.
Much broader. Now it encompasses everyone. Generation companies, gencos, transmission companies, transcos, distribution companies, discoms, and crucially, the prosumer. The whole ecosystem is involved.
Which raises another question. How has our approach to the smart grid changed over that last decade? What's different today compared to, say, 2010?
I think the biggest change is the depth and pervasiveness of the information and communication technologies, ICT. A decade ago, maybe it was more about specific applications, like smart meters or substation automation and isolation. Today, it's about integrating everything. It's about pervasive sensing, ubiquitous communication, big data analytics, AI, cybersecurity woven throughout. The ICT layer is much more central and comprehensive now. It's the glue holding it all together and enabling much more sophisticated functions.
Okay, that makes sense. The pervasive digital layer. Now, in the slide, you can see various definitions from different organizations like IEEE, DOE, AT Kearney. They might use different words, but you said they point to the same fundamental approach.
Exactly. It's like they're describing the same elephant from slightly different angles. Let's look at a few.
Okay, the IEEA.
The International Energy Agency defines it as an electricity network that uses digital and other advanced technologies to monitor and manage the transport of electricity from all generation sources to meet the varying electricity demands of end users. Key takeaways: digital tech, monitoring, management, handling diverse sources and varying demand. It's about visibility and control.
And the US DOE.
The U.S. Department of Energy's definition is a bit longer. It talks about bringing utility electricity delivery systems into the 21st century using computer-based remote control and automation. It highlights two-way communication technology and computer processing, noting these aren't new tech overall, but new to the grid at this scale. And it emphasizes benefits like energy efficiency for both utilities and consumers.
So automation, two-way comms, efficiency.
Right. And then A.T. Kearney offers a really concise one. A smart grid refers to a modernized electricity network that monitors, protects, and optimizes the operation of its interconnected elements. Short, sweet, but covers the key functions. Monitor, protect, optimize. Modernization is key.
So if you synthesize those, what's the common thread?
The common thread, really the undeniable truth, is leveraging advanced ICT. Using digital communication, sensors, computing, automation, to make the electrical system more observable, more controllable, more efficient, more reliable, and more resilient. It's about applying digital intelligence to the physical power grid.
Okay, so given those slightly different takes, what's the simplest, most practical way for us to think about it? In the slide, you can see a sort of layman's summary.
Yeah, cutting through the jargon is helpful. So while there isn't one single standard definition, and it's still evolving, broadly we can say a smart grid is a power system that uses some ICT tools, information, communications, technology, to improve the efficiency, reliability, economics, and sustainability of generating, transmitting, or distributing electricity, or all three.
ICT is the key enabler.
It's the absolute core. And it applies across the board: generation, transmission, distribution. Now, here's a really important clarification. In fact, most of the work that's already been happening for years in power system modernization, things like substation automation and distribution automation, that's now largely being folded under the umbrella term smart grid.
Ah, so it's not all brand new.
Not entirely. Of course, there are new capabilities being added, especially around that deep ICT integration, two-way communication, and consumer interaction. But a lot of it is an acceleration and enhancement of ongoing modernization efforts, just rebranded and supercharged with digital tech.
That's a really useful perspective. So thinking about this whole transformation, is it just a requirement, something utilities should do, or is it an absolute necessity now? In the slide, you can see this idea of grid modernization toward smart grid.
That's a great question, and the answer is often context dependent. The urgency, the feeling of necessity, really differs country by country. It depends on how smart or robust their existing grid already is.
Developed versus developing nations, for example.
Exactly. And in a developed country with a relatively solid, albeit aging grid, modernization might feel like a continuous improvement requirement needed to stay reliable, integrate renewables, improve efficiency. But in a developing nation facing soaring demand, high losses, maybe unreliable supply, there it's often an absolute necessity. They need to leapfrog to modern solutions to meet basic needs and enable growth.
But the characteristics are the same regardless.
Fundamentally, yes. A modernized grid, moving towards a smart grid, is always characterized by the use of digital ICT. It's designed to manage that bidirectional flow of data between users and operators, and the bidirectional flow of power between centralized generation and all those distributed resources. Those two bidirectional flows are key.
And the ultimate goal?
The goal is always to address those grid challenges we talked about: reliability, efficiency, renewables, integration, etc. But to do it at the minimal cost. It's about getting the most bang for your buck, maximizing performance and value.
So what enhanced capabilities does this modernized grid offer?
This is where it gets exciting. A truly modernized grid should be able to accommodate all generation and storage options, seamlessly integrate everything from nuclear to solar to batteries, optimize energy efficiency and asset utilization, minimize waste, use existing wires and transformers to their fullest before building new ones, avoid that empty 10-lane highway problem, improve power quality, deliver that stable voltage and frequency modern devices need, self-heal, this is huge, automatically detect faults, isolate them, and reroute power to restore service quickly, minimizing outages. Imagine the grid fixing itself. resist physical and cyber attacks, crucial for security and reliability in today's world, and enable new business solutions in a more open market. This includes things like demand response (DR) programs where you get paid to adjust your usage, and virtual power plants (VPPs), where thousands of small resources like home batteries or EVs are aggregated to act like one big power plant, providing services back to the grid.
That vision of a self-healing, adaptive, resilient grid is really powerful. So how is this actually being built? In the slide, you can see the smart grid broken down into key segments or design considerations. What are they?
Right, it's helpful to think about it in major functional blocks. The slide shows three main segments. A, optimization of grid monitoring and control. B, consumer-enabled grid management. And C, enhancement of network capacity.
Okay, let's unpack segment A, optimization of grid monitoring and control. What does that involve?
This is all about getting better visibility and control over the grid in real time. It means deploying advanced sensors and IT solutions for things like wide area monitoring and control at WAMC, seeing the big picture across regions and distribution automation, DA, controlling things down at the neighborhood level. Think sensors everywhere providing data.
Well,
It includes enhanced control of dispatchable power plants so they can react faster. Improved electricity flow routing, using algorithms to send power the most efficient way and avoid bottlenecks. Using predictive algorithms based on data analytics and AI to forecast demand or anticipate equipment failures before they happen. Moving to condition-based maintenance, fixing things when data says they need it, not just on a schedule. And a key part of DA smart reclosers that enable that self-healing function on distribution lines, automatically isolating faults and restoring power to unaffected areas.
okay, that covers monitoring and control. What about segment B, consumer-enabled grid management?
This is where the customer comes in. It starts with intelligent end-user devices, smart thermostats, smart appliances, and advanced metering infrastructure, AMI, which includes smart meters.
The meters that allow two-way communication.
Exactly. They provide real-time data to the utility and can receive signals from the utility. This enables dynamic demand response (DR) programs, things like time-of-use pricing or direct load control to manage peak demand. The bidirectional meters also support net metering, so you can get credit for exporting solar power, and potentially vehicle-to-grid (V2G) programs, where your EV could actually send power back to help the grid.
Making the consumer a prosumer.
Precisely. Prosumers as local suppliers of power and storage. And AMI also includes automated meter reading, AMR, which cuts utility operating costs and helps detect electricity theft, improving overall economics.
Got it. And the final segment, C, enhancement of network capacity. This sounds like the physical infrastructure.
It is. Sometimes you just need bigger pipes or smarter pipes. This involves new infrastructure options like ultra-high voltage UHV lines, advanced DC cables, maybe even superconductors eventually. These can carry more power with lower losses, especially over long distances.
Useful for offshore wind.
Yeah. Very useful for remote offshore wind connections and also for interconnecting asynchronous grids like linking national grids that aren't perfectly synchronized. Another key tech here is dynamic line rating. Instead of having a fixed capacity limit on a transmission line, you use sensors to see how much power it can actually carry based on real-time conditions like wind speed cooling the wire.
So you can push more power through existing lines safely.
Exactly. It lets you squeeze more capacity out of existing assets, potentially delaying or avoiding the need for expensive new lines. It's about being smarter with the infrastructure you have.
This is incredibly comprehensive. It really changes the game. Thinking about all these capabilities, how does this fundamentally alter the day-to-day work for electrical engineers out there?
Oh, it's a massive shift. Engineers will need to be much more data savvy. They'll be working with complex communication systems, cybersecurity protocols, advanced analytics, automation software. It's less about just the physical hardware and more about the integrated electro-digital system. It requires continuous learning, cross-disciplinary skills, blending power engineering with IT, comms, data science. The job becomes more about system optimization and data interpretation alongside the traditional roles.
A big evolution in skills needed. Now, in the slide, you can see this representation of various key smart grid technologies, and then another slide showing it as a big jigsaw puzzle. What's the takeaway from those visuals?
Yeah, those slides really emphasize the integration aspect. What's fascinating, as we've discussed, is that it's not just about having these individual cool technologies, advanced sensors, smart meters, FEX-UTS devices. The real power, the real complexity, comes from how they all fit together, how they communicate, share data, and work in concert.
Like puzzle pieces.
Exactly like puzzle pieces. Each technology, Each system needs to seamlessly connect and interoperate with the others to create the overall picture, the functional smart grid. It highlights the interdependencies. A smart meter is only truly smart if it can talk to the utility systems, which can then talk to the grid control systems and so on. It's about building that holistic, integrated system.
And making all those pieces fit, making sure they can talk to each other reliably and securely. That brings us to standards. In the slide, you can see a list of key smart grid standards. How critical are these?
Absolutely critical, foundational. Without standards, you'd have chaos. Imagine trying to build the internet without common protocols like TCP/IP. Standards ensure interoperability devices from different vendors can work together. They ensure reliability and security by defining common requirements and protocols. They basically provide the common language the grid components use to communicate. You simply couldn't build a large-scale, multi-vendor smart grid without them.
Okay, let's touch on some key ones listed. What about the IEC standards?
Right. The International Electrotechnical Commission has several crucial ones. IEC 61850 is huge for communication within substations, letting protection relays, controllers, etc. talk to each other. It's key for substation automation. Then you have IEC 61968 and IEC 61970, which are more about integrating different software applications at the utility level, making the energy management system talk to the outage system, for instance. IEC 62351 is vital. It focuses specifically on cybersecurity for all this power system communication. IEC 6205104 is a widely used protocol for SCADA systems real-time data exchange between control centers and remote sites like substations.
What about IE standard?
IE, the Institute of Electrical and Electronics Engineers, also has key standards. IE 1547 is absolutely fundamental for connecting distributed energy resources, DER, like solar and battery safely and reliably to the grid. It covers how they should behave when connected. IE 2030 provides a higher-level interoperability framework looking at the integration of power systems with IT and communications. And IE 1901 deals with broadband over power line BPL communication, using the power lines themselves to carry data.
And there are others mentioned too. NIST, OpenADR.
Yes, organizations like NIST, the U.S. National Institute of Standards and Technology, have developed comprehensive interoperability frameworks and crucial cybersecurity guidelines like NIST IR 7628. Then you have application-specific standards like OpenADR 2.0, which is widely used for automating demand response programs, and protocols like OSGP used in smart metering and grid device communication. It's a whole ecosystem of standards working together.
Wow, that's a lot of standards. It really underscores the complexity. So given all these different standards, how do engineers in the field actually ensure compliance and make sure stuff from different companies actually works together in a real project? That must be a major headache.
It is a major challenge, no doubt. It requires a lot of expertise. Engineers rely heavily on testing and certification. Devices and systems go through rigorous testing against these standards in labs. Vendors often participate in interoperability plug fests to test equipment together. Strong system integration planning is crucial upfront in any project. Pilot projects are often used to test things in a controlled environment before full rollout, and engineers need to constantly stay updated because the standards themselves evolve. It's a continuous process of specification, testing, validation, and learning.
Makes sense. It's an ongoing effort. So finally, as we wrap this up, the last slide has a simple but vital message. Adopt smart grid with careful approach. Why end on that note of caution?
Because it's crucial context. This isn't magic. Transforming the grid is a massive, complex, expensive undertaking. It's not a simple install software kind of upgrade. It requires meticulous planning, thinking years ahead. It requires significant investment, often billions of dollars. Cybersecurity has to be baked in from the start, not bolted on later, because the attack surface grows immensely, and it usually needs a phased implementation strategy. You don't rip out the old grid and plug in a new one overnight. You do it piece by piece, managing the risks and ensuring stability throughout the transition.
So for our audience of engineers and students,
For you, it means understanding the big picture. It's not just about knowing the tech specs of a smart meter or a relay. It's about understanding the strategic drivers, the economic constraints, the regulatory environment, the security implications, the integration challenges. You need that holistic view to design and implement these systems responsibly and effectively. It's about careful, considered engineering.
what an incredible journey through smart grid concepts. We started with the core objectives that Co-Optimization Balancing Act looked at the amazing traditional grid, but also its limitations facing today's challenges. We unpacked all those changes, renewables, prosumers, bidirectional flow that are driving this modernization. We clarified what smart really means here. The ICT layer looked at the different definitions converging and got a practical working definition. We explored the key segments: monitoring, consumer engagement, capacity enhancement, and the vital role of standards.
Yeah, covered a lot of ground.
We really have. We've seen the grid evolving from that centralized, one-way reactive system into something decentralized, two-way, data-rich, and hopefully much more responsive and resilient. We hope this exploration has given you, our listeners, a clearer roadmap, not just what the smart grid is, but why it's happening and what it means for electrical engineering.
And maybe just one final thought to leave everyone with. As we build this increasingly intelligent grid, connecting billions of smart devices, processing vast amounts of data, what are the maybe unforeseen societal or ethical implications? Beyond just keeping the lights on, how might this deep interconnection affect privacy, equity, or even community dynamics? That's something we as engineers and as a society will need to grapple with as this technology continues to evolve.
That is a powerful question to ponder. Thank you for joining us on this exploration of smart grid concepts. We definitely encourage you to keep digging into this fascinating and absolutely critical field.
Do come back for new videos on power system.